Hey, welcome back to Fan Physics. In this video, we are going to look into the mathematical aspect of half-life. So, let's begin here. I'm actually going to do a full-on lesson on this since it's not a lot of content. It was just mostly utilizing your understanding of half-life and maybe applying some math. So for an HL student, what do you need to know? In this video, I'm going to cover the idea of this, first of all, the mathematical model for radioactive decay. I'm going to show us a little bit of how to derive some of the equations. You are not required to do extensive derivation, especially with the calculus portion. However, I would say it is very useful to be able to figure out what the half-life equation is, and as well as showing the relationship between the decay constant and the activity. What else I will be featuring in this video is to show you how to figure out the slope, as well as the y-intercept on a graph produced by, say, taking the natural log of the equation. So it is required that you understand or are very flexible with doing working with logarithms and natural logs. And of course, applying to a real question. So let's begin. All right, so this first part, I'm going to introduce the concept of these symbols, what the decay constant is, what the activity is, a little bit of relationships, and a little bit showing you how to basically derive that equation, the equation that is in your data booklet, okay? So if you want to, you could just listen on to the first part. The second part, since it's the calculus portion, I believe that is optional for us in terms of knowing that for the exam. So based off of experiments, we have generated a relationship. The relationship is this the rate of decay, which uses these symbols here. So this is the rate of decay. The rate of decay is directly proportional to the number of radioactive nuclei. So meaning that the more radioactive nuclei there is, the higher the rate of decay. Meaning that over time, the rate of decay will slow down as there are less radioactive material. So the actual form of what that takes on looks like this, in which n is the number of radioactive nuclei, but there's also this little constant here called the decay constant, meaning that the greater the decay constant, the greater the rate of decay, which also means for different radioactive substances, this decay constant will be different because the nature of the decay, the rate of decay will also be different. There is this negative sign, meaning that essentially, whenever there is a decay happening, it's talking about the loss instead of a gain. So it means that you're losing radioactive nuclei over time, which is what that negative sign means. So what is the decay constant? Decay constant is it's a probability, or it's a probability that a nucleus will decay in a unit of time. So essentially, the units are time to the power of -1. It's per unit of time. So it's a probability. It's the chance of something that will decay within 1 second or a day or whatever that is. So usually it's measured in units of a second to the power of -1 or per second. The other term that you need to be aware of is the activity of the sample. The activity of the sample is essentially this over here, delta n over delta t. It is the rate of decay. So this negative just means loss, okay? It's not gain or anything, okay? So that's because activity is equivalent to delta n over delta t, the activity is also equal to the decay constant times n, which comes directly from here. So if we write this down a little bit more, this is just equal to negative delta n over delta t. Okay, so A, activity, has all those representations. A recap from before, the activity is measured in Becquerel, which is the amount of decay, the number of the number of decays happening per unit of time, usually in seconds. So there you go, number of nuclei decaying per second. Okay, so that is the unit of Becquerel, which you might see in questions. Okay, also keep in mind that the initial activity of a sample is equivalent to the decay constant times the initial amount of radioactive nuclei. Okay, so keep that in mind as well. So this is the all of this stuff is definitions. So I'm gonna go on into tutorial questions number 1. I'm gonna break this lesson up into 3 videos. So this one I'm just gonna cover 1. Next video I'll do 2, 3, and 4, and then last I'll do 5 and 6 for examples. Okay, so let's begin. Okay, so we're essentially going to show that this equation, which is the decay equation, is going to give us exactly what we get in our data booklet, which is this guy over here. N is equal to n naught e to the negative lambda t. So we want to show this. Okay, so how to show that, we will start off with this guy over here. So we want to, the question tells us, gives us some instructions on how to do that. We're going to integrate it from the beginning of the decay, so when t is equal to 0, and this is when the initial number of radioactive nuclei is n naught, or think of it as the initial. For the initial number, you go to some time in the future t, and some amount of nuclei left over n. Okay, so the first thing we have to do before we take the integration is we need to combine terms that, combine like, not like terms, but symbols that are similar. And what I mean by that is, if I had to convert this to a differential equation, it's going to look like this. dn over dt equals to negative lambda n. So we have to combine the n's together before we take the integration, otherwise it's going to be very messy. We also need to put delta t on the other side in order to integrate them separately. It doesn't really matter what the decay constant goes, since it's just a constant, but I think I like it on the right side. So if we do a little cross multiply, this is going to give us, or cross divide, this is going to give us delta n, and this n over here, this guy is going to get divided to the bottom. Actually here, let's just write it out. This goes to the bottom, dt goes to the top, which then cancels this guy down here. Okay, and this is going to give us dn over n is equal to negative lambda dt. Okay, now we can take the integral, and for n we're going to take the integral from the initial, which is when it was all parent nuclei, to sometime later, which is n number of nuclei are still radioactive. For time, this is going to be the beginning of time, which is 0 t, and then to sometime later t. Okay, so to find to integrate this, dn over n, to find the antiderivative of that one is just ln of n. So the derivative of ln n is just 1 over n. So this one, we're integrating it from n naught to n, okay? The other side, we're going to integrate time. But before we do that, we know that lambda here is a constant. We can just put negative lambda on the outside and just integrate from 0 to t for dt. And that's just t, essentially. So, so we have negative lambda t integrating from 0 to t. Okay? So after we do that, we're going to get ln of n, which is that one, and we're going to subtract ln of, sorry, that's an n naught, ln of n naught, okay? So we're going to take the difference there, and then same thing here, negative lambda t, which is going to be t value, minus the negative of lambda t is 0, so times 0, and whoopee, this goes away, this term just goes away to 0, which means we're going to be left with, okay, so more space on this side, and so here you're going to really need to know your natural logs, you need to know your exponent laws, but for logs. And we know if we're subtracting two natural lns or just logs, it's the same as combining them, but you have n divided by n naught. It's just like whenever you're dividing exponents, referring back to exponent laws, like if I have x to the power 5 over x to the power 3, if you have to divide this out, this is just 5 minus 3, which is exponent of 2. So using your exponent laws, this is very similar to that. So subtraction is equivalent to division, dividing your powers together, okay? So here we have ln n over ln n naught, and this is equal to negative lambda t, okay? So that's on the other side. Okay, we're not quite done yet, okay? Using the definition of the natural logarithm, which I've kind of just shown a rough work over here, so that if we want to express use e to the power of x is equal to some number y, we're basically going from this form on the bottom to the top form, which kind of looks like this. So what we want to do, imagine, I kind of think of it this way when I do this. I imagine that there's an imaginary e down here, and then I take e to the power of x is going to give me y. So I'm going to do that here, in which this e to the power of negative lambda t is going to give me n over n naught. Okay, so that's what I get, based off the definition of a logarithm. Okay, so if I just multiply n naught to the other side, then I am going to get, finally, and I'm going to put n on this side, so I'm going to move the equation, reverse the equation a little bit. It's going to give me n equals to n naught e to the power of lambda t. And there we go. This is our relationship that we find in our data booklet, and which we're going to always use. And from this, we can incorporate activity and other nice things as well. So in the next few videos, we are going to use this equation to do our bidding. So this is the end of this video. Please stay tuned for the later half of this tutorial and as well as more examples. Thank you for watching. Good luck, and Fat Mama Physics signing out.